All right, lesson 5.6. This is going to be our last part for chapter 5 here. You can see the objectives. We're going to look at those in a couple different ways. So first thing we get into is vertical and horizontal asymptotes. And probably the best example of this is if you look at the graph of f of x equals 1 over x. So here's the graph. I just put it on Desmos. I'm going to use this. So realistically, what this would look like is it'd be f of x equals 1 over x. We have a horizontal asymptote and we have a vertical asymptote. So here's a horizontal. And then we could go red. Here's your vertical. And so first thing is just the idea of the notation. As x goes to infinity, so as x is approaching as infinity, what is y doing? So as x goes out, oh, we can't do that, shoot. As x is going further and further, it's just going to show up, I don't know. As x goes further and further, it gets bigger and bigger. What is the y value doing? Well, the y is going to 0, right? So technically we would say as x goes to infinity, y, or sorry, it should be f of x goes to 0. What happens as x goes to negative infinity? So that's over on this side over here. So as x goes to negative infinity, it gets bigger and bigger and bigger and bigger. So as x goes to negative infinity, what is y doing? Well, y, or f of x, is going to 0. Okay, that's along the horizontal. The vertical, the way we'd see the vertical is, okay, as x is going to 0, but it's approaching 0 from the right side. It's on the right side of 0. So, here's 0. If it's on the right side, that's 0 positive, 0 with a little plus sign. And if it's coming from the other way, we're on the negative side, so that's 0 approaching from the left. So as x approaches 0, notice this asymptote, it never actually crosses. It just gets super and super close. As x goes to 0, what is y doing? Well, as x goes to 0, f of x is going to negative infinity. And we're going from 0 from the right, so we put a little plus sign. Over here, on the other side, as x approaches 0 from the left, f of x goes to negative infinity. So the minus sign out in front means negative infinity. The sign on the top corner, on the top right corner, is telling you which direction it's approaching from. Because notice this, that as you approach 0 on the x-axis, in one way it's going up, and if you come from the left side, it's going down, so it's going opposite directions. Okay, I'm going to show you one more here. Okay, now I added a second graph, and so I added in the blue, and I want you to notice the red, which is the 1 over x. I want you to notice how as it goes to 0, 1 goes up, 1 goes down. Okay, that's that's an odd piece, right? X to the first, that's odd. X to the second, I want you to notice how as it approaches from the left and the right, the blue one goes in the same direction. So I'm going to get rid of the red one so you can just see the blue one there. And what I want you to notice is as x approaches 0 from the left, it goes to positive infinity. As x approaches 0 from the right, it goes to positive infinity. So as we're getting stuff set up later on, you'll find that anytime they're approaching an asymptote from left to right and they go in the same direction, then that's going to be something squared. If they go in opposite direction, then it's a linear first degree. Okay. So that took care of the majority of that stuff that is going through here. So here we go. Let's see. Horizontal asymptotes, vertical asymptotes. I think we hit. We'll talk more about it later. I think we covered a lot of that. Here it says use arrow notation to describe the end behavior and local behavior of the function graph. So this time you can see we've got a couple asymptotes. We got a horizontal and a vertical. And so the asymptotes we want to look at is going to be this horizontal one. That's going to be at 4, right? So what is happening as x goes larger, so as x is going larger and larger and larger, so like at 5, at 6, at 7, what is the y value doing? So as x goes to infinity, then f of x is approaching the number 4. As x approaches negative infinity, so like -2, -3, -4, so the further and further negative infinity on the x value, where are we going to? Well, as x approaches negative infinity, f of x is still going to go to this value of 4. So that's your horizontal. Your vertical, the local behavior. So as x, that would be this one here, this is your vertical, it's at 2 here. So as x is approaching 2 from the left, okay, so as x approaches 2 from the left, so we're going this way, where's the value going? Well, it's going to negative infinity. So f of x goes to negative infinity. As x approaches 2 from the right, so we're going towards 2. We're coming from the right side. Where are we going? Our function is going to infinity. Here, number 2 says sketch a graph of the reciprocal function 1 over x, shifted 2 units to the left and up 3 units. Identify the horizontal and vertical asymptotes. So remember, like, this is the 1 over x over here just shifted. So if this is my x and y axis, and you're going to find, like, when we graph stuff, if you don't have graph paper, you can just sketch it. We want it shifted 2 units to the left. So normally in the graph we started at, our asymptote would be at zeros. So we're going to shift it 2 units to the left. So I'm going to make them yellow just so they're just highlighted. So that's going to be one of my asymptotes. And then we want to shift it up 3 units. So that graph is going to look like this. Right? Now, let's talk about how do we actually get that function. Well, if one of my x or my x values here, the vertical asymptote, that means if this is a vertical asymptote, that means that x cannot equal -2. That means that x plus 2 would have been 0 at, like, in the function. So we know that f of x is 1 over x plus 2. And then how did it shift? It shifted up 3. So that's where we put plus the 3. Okay. The rational function. So your rational function is basically just the idea of a ratio. Your q cannot be 0 because you can never divide by 0, right? And so it's just a polynomial over polynomial. We've dealt with this already a little bit, we've dealt with the polynomial piece, but now we're just putting it as a fraction. So example number 3, it says a large mixing tank currently contains 100 gallons of water into which 5 pounds of sugar have been mixed. Okay, so a tap will open, pouring 10 gallons per minute of water into the tank. At the same time, Sugar is poured in the tank at a rate of 1 pound per minute. Find the concentration, pounds per gallon, of sugar in the tank after 12 minutes. So what are we dealing with? Well, we're dealing after 12 minutes. So our variable is going to be t for time. The water, our water started out with 100 gallons when t was 0. When t was 0, we had 100 gallons of water. And then we added in 10 gallons per minute, right? So our water, after 1 minute, we'd have 100 plus 10, or after 3 minutes, we'd have 100 plus 30 gallons, so 130 gallons of water. The sugar, we started out with 5 pounds of sugar when t was 0, and then we're adding in 1 pound per minute. So plus 1 t, or just t. Okay, now it says find the concentration rate of pounds per gallon. So pounds per gallon, that's the sugar per water, if I think about it that way. So that means it's just a fraction. So sugar, so 5 plus t over 100 plus 10t. This is the concentration, so we'll call it C. So that's our formula. C of 12 is going to equal 5 plus 12 over 100 plus 10 times 12, which is going to give you 17 over 220 if you just plug it in your calculator. So is that a greater concentration than at the beginning? Well, at the beginning, that would be C of 0, right? Because your minutes were 0. So that would be 5 over 100, or 1/20th. And if you divide them out, you find out that 17 over 220 is greater than 1/20th, just by not a whole lot, but a little bit. So is that a greater concentration than in the beginning? Yes, it is greater now than what it was. Okay. So the domain of a rational function includes all the real numbers except those that cause the denominator to be equal 0. Because remember, you can't divide by 0, right? We cannot have the denominator be 0. So to find the domain, that's where we're going to say that the denominator, the x squared minus 9, we're going to see when does it equal 0. So x squared equals 9, and x is going to equal plus and minus 3. So the denominator, x is an element of the real numbers, such that x is not equal to plus and minus 3. Or you can just say that x is all real numbers except x is not equal to plus and minus 3, however you want to state it. That's your domain. Find the vertical asymptotes. So now if we think about that, what that does is these become the idea of vertical asymptotes. But there's a little bit of a hitch, and we should come back to number 4, because there's a hitch in there when we talk about vertical asymptotes, and maybe you see it. But when we look at a vertical asymptotes, that happens in the spots where your denominator is 0, right? So here, our denominator, 2 minus x squared, that factors into 2 and 1. And then we'll want negative x and positive x, because that gives me, or did I do it backwards? Oops, this is got to be positive. This has got to be negative. So that I get negative 2x, positive 1x gives you a negative x. Okay, so then this equals 0. So then that is going to be the fact that 2 plus x equals 0, and 1 minus x equals 0. So x equals negative 2, and x equals 1. So those become your vertical asymptotes. Your vertical asymptotes, so if this is my graph, my one of them is at x equals negative 2. If it's a vertical line, remember, then it's simply x equals negative 2. That's literally the equation of the vertical asymptote. And then x equals 1. Those are your asymptotes. Now, if we go back up to number 4, what's going to happen here? Well, number 4 becomes something called a whole. So if we look at this equation, so I have x plus 3 over x squared minus 9. Do you agree that that's x plus 3 over x plus 3 times x minus 3? So although we said that the denominator cannot be negative 3 or positive 3, do you see how we could knock that out? This part is the fact this is what we call a whole, because it factors out. So as you start simplifying your expression, it goes away. And now your only issue is just that x can't be 3. But reality is there's a whole right here at negative 3. Because if you were to plug negative 3 in, you would get this part going to 0 in your denominator, which would be an issue. So we would call x equals negative 3 a whole. And we'll come back to that in a minute. And that's what you call, that's actually what you call the removable discontinuity. So remember, we had 2 issues at 3 and negative 3. But when I factored the numerator and the denominator, I had a common factor. So that would have allowed just for x to equal negative 3, or x minus 3 to be the only part. So then this then becomes 1 over x minus 3, which then you'd say, oh, x just cannot equal 3. Well, this is kind of what they've always taught you in, like in middle school, maybe when you would have done this. But the reality is we just canceled this top and bottom out. Well, that created an issue. There's something happening there. That's kind of like if you were to have 4x over x, okay, and then you reduce it and you say, oh, that's just 4. That's not really true because your denominator, x, should have never equaled 0. But there it could be. So there's a little bit of false guidance that you've learned in the past. And so this is one of them. Anytime you have that common factor, that's going to be called a whole. So here, find the vertical asymptotes and removable discontinuities. So our vertical asymptotes, when we look at this, we can see that the x minus 2 is going to cancel. So if x minus 2 equals 0, x equals 2. This is a removable discontinuity. Okay. Then your asymptote becomes x plus 2 equals 0, so x equals negative 2. That would become your asymptote.